All right, so 4 is curve sketching with extremas. Okay, so we are going to basically use the idea of concave max, concave up, and concave down to find maximums and minimums, and with those inflection points become more accurate with our graphs. Okay, so here's some basic steps for finding accurate pieces of a graph. Okay, so we're going to start with finding the domain. We're going to reduce the function if we can to find holes and vertical asymptotes. Okay, we'll find our x and y intercepts. We'll list our end behavior. Remember that that's horizontal asymptotes. Okay, you can check for symmetry, and then we can look for increasing and decreasing intervals. So we're going to be using our first derivative for that, for critical values, for maximum and minimums. And then for 8, we'll use our second derivative for concavity and points of inflections. Okay. All right, so here's our first example. It is a rational function. Okay, so we're going to start by taking the original function and listing the domain. So a domain for this one would be any value that makes the denominator 0. Okay, so if you set this equal to 0, you end up getting a square root of a negative. So basically, there's no value that makes this denominator 0. So there's no restrictions on the domain. So we can say all reals or from negative infinity to positive infinity. Okay, vertical asymptotes. Since there's no restrictions on the domain, there's no vertical asymptotes. So we can say none. Again, no holes, because that would be something that canceled with the top. For x-intercepts, okay, so x-intercept, we just take the function and we set it equal to 0. So kind of mentally, if we set this equal to 0, the denominator goes away. And so we have 0 equals 2x cubed. So the x value for that would be 0. So we have an x-intercept at 0. For y, we plug 0 into the x. So if I plug 0 in, I get 0 over 1, and 0 over 1 is 0, which would make sense if it's at 0. Okay, for end behavior, so I'm thinking horizontal asymptotes. For horizontal asymptotes, is this function bigger on the top or bigger on the bottom? And since it's bigger on the top, we have a slant. Okay, so I know it's going to positive infinity or negative infinity depending on my end. So if we think about the right end, the right end is as x goes to infinity. So if I plug in a positive number into the top, I get a positive out. And if I put a positive number into the bottom, I get a positive out. So I get a positive number. So that's going to go to a positive infinity. For my left end, on my slant going the other direction, if I plug in a negative number, I would get a negative over a positive. So a negative over a positive is going to go to negative infinity. Okay, for symmetry, you can plug in a negative x value into both of the x's. So if I plugged in a negative x value, I'd get basically a negative on the top here, negative 2x cubed, and then on the bottom, the negative would cancel because it would immediately be squared. So if I compare that to the original, I have basically a positive version and then a negative version. So that's going to be symmetrical over the origin. Okay, because it's exactly opposite. So the idea of that one was if I have f of negative x, that would still equal the f of x. Okay, so now we're dealing with relative max and min. So we're going to get relative max and mins from our first derivative. Okay, so they give us this first derivative. And first we want to come up with any critical values. Okay, any value that makes the denominator 0, which we talked about in the previous case, we're good there. But if we set this equal to 0, we end up getting one critical value. Okay, so we get a critical value, we get 0, and if you set this one equal to 0, you get negative 3, and then the square root of negative 3 is an imaginary value. So you only get one critical value. So our one critical value is at x equals 0. So I would do my number line test and my f derivative to check out the slope of this function. Okay, so again, if I'm using my derivative, I pick a number that's less than 0. So if I plug in, let's just say -1. So -1, if I plug that into my derivative, I'm going to have a positive and then times a positive, which is a positive on the top over a positive. So I get a positive over a positive for that. If I plug in a +1, I get a positive over a positive, and that's still going to be, well, positive. Okay, so the idea of this function is it's going up and it's going up again. Okay, so something's happening here at the 0. So now I'm going to do the second derivative. So if I use my second derivative, my critical values for that one, the denominator doesn't give me a critical value, but the top I have 0, and then I also have, if I add 3 and take the square root, I get plus or minus the square root of 3. Okay, so for this one I get 0 and plus or minus the square root of 3. So if I do my number line test here, so I have a negative square root of 3 and a positive square root of 3 and 0 smack dab in the middle, I can do my number line test. Okay, so a value that's smaller than a square root of 3, let's try, how about just -3. So if I plug -3 into my second derivative, I'd have a negative, so that piece would be positive. And then a -3 squared would be 9. 9 minus 3 is positive, so I have a positive times a positive, so I get a positive on the top. And then on the bottom, I get positive there, so I get a positive over a positive, which makes a positive. Okay, a value between a negative square root of 3 and a 0 would be like -1. So if I plug -1 in, I get positive for that first piece, and then I got 1 squared, so 1 minus 3 is negative, so I get a positive times a negative, so I get a negative on the top, positive on the bottom. So negative over a positive, so it's going to be a negative. If I plug in a +1, I would get a negative times a negative. So that would be a positive. A positive over a positive gives us a positive. And if I plug in +3, let's say I'd get a negative. Negative times a positive, so that would be negative over a positive. Negative over a positive is a negative. Okay. All right, so how does all of this information play out? Okay, remember that anything that goes from a positive to a negative, remember we're doing concavity here, is a point of inflection. Okay, so I end up with 3 points of inflection. Okay, so I think that was the last thing here, points of inflection. So I have, oh, I guess it says points of inflection. Let's see, we got one at negative square root of 3, and if I plug negative square root of 3 into the original to find its corresponding y value, I will just tell you that you get -3 square roots of 3 over 2, which we could convert that to a decimal. If you plug 0 in, because it's our other x value, 0 into the original, I would get 0 over 1, which is 0. And then if I plug in the positive square root of 3, I end up getting the positive version of the other over 2. Okay, so now as far as my relative max and min, going back to my red piece right here, it's always increasing. Okay, so if the function is always increasing, I cannot have a max or a min. Okay, so I have no max and no min. Okay. All right, so now I'm going to take all of this information and graph it. Let's see, let's use red. I can start with some points. I don't have any asymptotes to draw. Remember, I have this slant thing going on. Okay, so I know I went through the origin because my x-intercept and y-intercept are 0, and I have a point of inflection there. Negative square root of 3, that's going to be like, let's see, a little bigger than 1, and then 3/2, so that's 3 right about there, and there. So those are those points of inflection. Okay, so remember that this function is always increasing, so that means from left to right we're going upwards. Okay, but if we think about the concavity, okay, when it's less than a negative square root of 3, we have a concave up. So there's going to be like this super slight happy face going on. Okay, and then from the square root of 3 to 0, there's a negative concavity, so it kind of goes down. Okay, and then from 0 to positive infinity, it has a positive up. So this piece right here looks pretty John Travolta-y. Okay, and then my last piece has a concave down effect. So it just basically goes a little down that way. Okay, so there is our first graph. Okay, so let's try another one, see if we kind of have this figured out. Okay, all right, so again we have a rational function. Okay, so we want to start with the domain. So I noticed the denominator of this can be factored. It's going to factor into x minus 1 squared. Okay, so immediately I see a value that makes this denominator 0. X cannot be 1. Okay, for a vertical asymptote, I'm checking to see if that cancels with anything on the top, and since it doesn't, I know there's no holes. There's a vertical asymptote at x equals 1. Okay, and maybe you want to say even more specifically that since it's squared, it happens to be an even asymptote. So if you remember, an even asymptote looks like a volcano, so they're both going upward or potentially both going downward towards that asymptote. Okay, x-intercept, if we set the function equal to 0, the denominator goes away, so we have 0 is equal to 3x minus 2, so there's an x-intercept at 2/3. Y-intercept, I plug 0 into the x's, so I'm going to have negative 2 over 1. So at negative 2. The end behavior, I'm thinking horizontal asymptote, so I'm looking at the values in front. It is bigger on the bottom, so bigger on the bottom implies that I go to 0. I have a horizontal asymptote at y equals 0, so that implies both ends are going to 0. Okay, so for symmetry, I'm going to plug in a negative x value and see if it's equal to the regular one or if it's opposite. Okay, so if I plug a negative in here, that's going to give me negative 3x minus 2, and I can even stop at that point. On the top, it is not the same and it is not exactly opposite. It's going to be totally different. So this is none. There's no symmetry for this. Okay, all right, so here we go with the relative max. So that's where my first derivative piece is going to come into play. Okay, on my first derivative, let's put this down here. On my first derivative, I have, first of all, a value that does make my denominator 0, which is 1. If I set it equal to 0, 0, let's see, I'd subtract 1 and divide by negative 3, so negative 1 over negative 3 is a positive 1/3. So for my first derivative, I have two critical values, so the smaller one is 1/3, the bigger one is 1. So if I do my sign test, a value less than 1/3 is 0, so if I go 0 into my derivative, I would get 1 or a positive over a negative, right? So I get a negative on that interval. If I plug in, let's see, a value that's between 1/3 and 1 would be, how about 2/3? So if I plug 2/3 in, I'd have negative 3 times 2/3 would be negative 2, and negative 2 plus 1 would be a negative. On the bottom, I have a fraction minus 1, which is going to be a negative. I'm going to get a negative over a negative to get a positive. And last interval, a value bigger than 1, so I have a 2. So if I plug 2 in, I'm going to get, let's see, negative 6 plus 1 is a negative on the top. And on the bottom, I get a positive. Negative over a positive is a negative. Okay, so remember, since my domain had a restriction, I have a vertical asymptote at 1. So kind of imagine there's this vertical asymptote at 1. I have a slope. So these are my slopes. I have a negative slope, positive slope, and then a negative slope. Okay, so that kind of is a really big help right there. We can go to the concavity. So now I'm looking at my second derivative. So my critical values of my second derivative. Again, we have 1 from that vertical asymptote, and if I set the top equal to 0, I get a critical value at 0. So for my second derivative number line, I have 2 critical values also. So let's see, if I do my number line test, a negative 1 plugged in, negative 1 would be a negative over a positive, so I get a positive for that one. Excuse me, a negative over a positive is a negative, excuse me. And then if I plug in a number between 0 and 1/2, 0 and 1, I could plug in 1/2. So a positive 1/2 plugged in is going to give me a positive over a positive. And then if I plug in something like 2, 2 is also going to give me a positive. Okay, so second derivative gives me concavity. So again, I have my vertical asymptote at 1. So I have a sad face, happy face, happy face. Okay, so kind of imagine my blue line is kind of, for the most idea, the right function, but with this curvature going on. Okay, all right, so if we take a look at this, let's go back to my blue to find my relative max and min. I have a right here, a minimum, so I have a relative min at 1/3. So if I plug in 1/3, 1/3 into my original function, 1/3 times 3 is 1, so I get 1 minus 2, so negative 1. On the bottom, oh boy, okay, I'm going to type that in the calculator. Let's see. I end up with negative 9/4 for that. Okay, looking at this, I have no relative max because there is no top piece. So then I have, for my point of inflection, I have a negative to a positive at 0. So I have a point of inflection at 0, so I'm going to say 0. If I plug 0 in, let's see, that makes negative 2. All right, here we go. So I'm going to draw my asymptotes, points that I found, and then see if I can kind of connect the dots. So I have a vertical asymptote at 1. I have a horizontal asymptote at 0. Okay, remember horizontal asymptote only tells you end behavior. That doesn't mean you can't cross through it in the middle here, which in fact this one does. I have an x-intercept at 2/3. I have a y-intercept at negative 2, so down here. Okay, if I plot my points, let's draw my points. Negative, or 1/3 and negative 9/4, so that's like negative 2 1/4. So that'd be just below here. Oops. You can kind of see it goes down and comes back up. And 0, negative 2 is also a point of inflection. All right, so here we go to draw this. Okay, so remember I have a horizontal asymptote, so I'm going to have this left side exists below because all my points are below, and it's going to get closer. So it's going to start going downward, and then when it hits -2, it's going to start curving back so that it's going to be a minimum point here at that blue spot. Then it's going to go back up towards my intercept and go infinitely high to my asymptote. So let's see if I can draw this. Okay, so it goes up. Okay, now on the other side of this asymptote, okay, I can use my slope and my concavity to draw this. Okay, I know I have a negative slope, a positive concavity, so it's going to be kind of like a happy face, but just one side of it. I'll go down, and remember my end behavior goes towards 0. Okay, that looks pretty good. So I could even be more accurate if I wanted to. If I could find a point in here to be a little bit more accurate, that would be, but that looks pretty good. All right, so we're cruising. Okay, so we got radical functions. All right, so we got square root involved, domain. So if I look at the bottom, is there any value that makes that denominator 0? And remember with the square root, the inside has to be greater than or equal to 0. If you think about this, x squared and then that's a positive number plus 2, you're going to get a positive number. So there is no domain restriction. So negative infinity to positive infinity. And since we have no domain restriction, there's no vertical asymptote, and there's no hole. X-intercept, if we set it equal to 0, we get 0 equals x, so there's an x-intercept at 0. We find our y-intercept, we got 0 over 0 plus 2, so 0 over, well, the square root of 2 is still 0. Okay, end behavior. Okay, so this is a horizontal asymptote. So remember with the square root, you have to do plus or minus. So you technically have two horizontal asymptotes. So we have a horizontal asymptote at y equals plus or minus 2. So what I want to do is figure out to the right, is it going to the positive or negative? So if I think about my right end, plugging in some positive number. So positive, we're going to have positive over a positive. That's going to go to a positive number. So since we have an option of 2 or -2, the right end is going to go to positive 2. So that pretty much narrows down the left side. Double check it though, we would get a negative, yep, negative over a positive. So that's going to a -2. Okay, so two horizontal asymptotes. For symmetry, if I plug in a negative x value, I'd get negative x over a positive. That's going to be exactly opposite. So that one is symmetrical over the origin. Okay. All right, so working on relative max and mins. Let's do the first derivative. First derivative, there's no value that makes the denominator 0, and if I set it equal to 0, I have 0 equals 2. So there's no critical values. So interesting, I think. Let's just say we throw any number in, so that means all of the values are going to all be increasing or all decreasing. If I plug, let's just say 0 in, I get 2 over a positive, so I get positive over a positive. This thing is increasing always. Okay, so it's always going up. Okay, which, can I have a max or min if it's always going up? No. So we have no max, no min. Don't have a lot to go off yet. Okay, so now let's use our second derivative and see if we have any critical values. Whoa. There we go. Again, no value that makes the denominator 0. Ooh, but this time if I set this equal to 0, -6 times 0, so I have one critical number here, 0. So 0. Okay, if I plug a negative number in, I would get a positive over a positive. And if I plug a positive number in, I get a negative over a positive, so negative. So concavity, we got a happy face and a sad face. but always increasing. So since we go from a happy face to a sad face, I have a point of inflection at 0. There's one point on the graph at 0. To find its corresponding value, I plug it into the original. So 0 over the square root of 2 is 0. All right, here we go. All right, so I have point at 0, 0. I have, oh, here we go, horizontal asymptote. So I have a positive 2, negative 2. Okay, so remember at the right end it's getting close to positive 2, so it's up here somewhere, and at the left end it's going down to negative 2, so it's, oh, okay, so if we start down here and we cross up through our point of inflection, it's going to continue onward. So this is going to look very much like a sideways John Travolta with our point of inflection. Okay, and that matches our concavity. We got a positive concavity between 0 and negative infinity, and a negative one greater than 0. Okay, all right, so your homework is to do problems 1 through 5. 1 through 5. Okay, so I'm actually going to continue on doing this, so you can stop the video if you want and go on your own, or you can continue watching and see if you can do this all by yourself or not. Okay, so the directions here say, without using a calculator, find our extremas, our points of inflections, and then sketch the graph. Okay, so we're going to make it very clear with justifications. We're going to find x-intercepts, check any restrictions for domains or asymptotes, and talk about end behavior. Okay. So for question number 1, first of all, do I have any domain restrictions? Okay, I would say no. So the domain can be from negative infinity to positive infinity. I know that this looks like a John Travolta. So right end goes to positive infinity, left end goes to negative infinity. Okay. Let's see if we have any relative maxes or mins. Oh, actually, let's find some x-intercepts real quick. Actually, that's not a very nice one, so I'm gonna leave it for now. I'll find it later if I feel like I need to. So let's go straight into a max and min. So my derivative of y is 3x squared minus 6x. If I set that equal to 0, I'm going to pull out a 3x, so I'm left with x minus 2. So I have two critical values at 0 and 2. So if I do that number line, okay, a negative 1 would give me, let's see, we got 3 plus 6. That's a positive number. If I plug in 1, I'd get 3 minus 6, that's negative. And if I plug in 3, I would get 27 minus 18, that's positive. Okay, so I can see that I've got boom, boom, boom. So I got a relative max at 0. So if I plug 0 into my original, I would get, let's see, 0 minus 0 plus 5, get 5. I have a relative min at 2. So 2, if I plug 2 in, let's see, 8. And 4, 8 minus 12 is negative 4. Negative 4 plus 5 is 1. Okay. Let's go to concavity. So that's second derivative. So my second derivative would be 6x minus 6. If I set that equal to 0, add 6, divide by 6, so we get a critical value at 1. So at 1, if I plug that in, let's see, if I plug 0 in, I'd get a negative. If I plug 2 in, I get a positive. So I have a sad, happy face, point of inflection at 1. So if I plug 1 back in, I would have 1 minus 3, so negative 2, and negative 2 plus 5 is 3. Okay, so that should be enough information. Excuse me. To graph this. So I'm going to start by graphing my points. So I have a relative max at 0, 5. So 1, 2, 3, 4, 5. Relative min at 2, 1. Have a point of inflection at 1, 3. Oh. Okay, and I know that this looks like a John Travolta, so the left arm was down and the right arm was up. Okay, so it's going to have, this is going to be a max, so it's going to kind of cross through. So I could find my x-intercepts if I wanted to find exactly where this crossed, but it's going to come through and then come back up, go up. So maybe if I wanted to be more exact, I could find that last intercept, but I think that's pretty good. That's pretty much answering all of the things that they want us to do. It says it's not necessary to find x-intercept. So I'm not going to do it if they say it's okay. Okay, so number 2. Okay, so for my domain, so I'm going to rewrite this real quick because I don't like the way it's written. Negative x cubed minus x plus 1. Domain, there's no restrictions. I know it looks like a John Travolta with his left arm up. Okay, so right end is going to negative infinity, left end is going to positive infinity. Okay, so let's go straight to finding any relative maxes and mins. So my first derivative, negative 3x squared minus 1. Set that equal to 0. So I add 1, divide by 3, negative 3. That's a problem. So I get no critical values. So if I do my number line test on that one to see if it's positive or negative, I'm going to make an educated guess here, it's going to be negative, but let's just double check. If I plug 0 in, I get a negative, so this is always decreasing. Okay, so we should have a point of inflection, where it does the little wiggle for the John Travolta. We need something to graph. Let's see, the second derivative is going to be negative 6x. So it's going to wiggle at 0. So critical value of 0. If I plug in a negative, you get a positive. If I plug in positive, you get a negative. So it's going to be like so. Okay, so I can get my point of inflection exactly 0, what? Let's see, 0, if I go back to the original, 0, 1. Okay, so I'll go like that. So again, maybe a x-intercept would be a little bit more helpful, but since again they don't ask for it, we're good to go. 3. All right, so this time we have a to the 4th power, x to the 4, so no domain restriction again. X to the 4th is going to be, end behaviors are going to both be up since it's positive, so I can say right end and left end both go to positive infinity. Let's do any max or min. So I take my first derivative, I get 4x cubed minus 12x squared. Set it equal to 0. Greatest common factor would be 4x squared. Be left with x minus 3. So critical values of 0 and 3. Okay, so left of 0, so if I plugged in -1, I'd get -4 minus 12, that's negative. If I plug in 1, I would have 4 minus 12, that's negative. If I plug in 4, I would get, I don't know, 4 to the 4th power, which has got to be bigger than 12 times 4 squared. So that's going to give us a positive. Okay, so we got negative, negative, positive. So we got a, right here, a relative min at 3. So if I plug 3 into our original, let's see. Three to the 4th minus 4 times 3 to the 3rd plus 16. -11. Okay. So I'm guessing this right here is going to be some kind of like point of inflection. Let's see if we're right. Second derivative would be 12x squared minus 24x. If I set that equal to 0, I can pull 12x. So I'd have x minus 2. So critical values at 0 and 2. 0, 2. So if I plug in -1, I get 12 plus 24, that's positive. If I plug in 1, I get 12 minus 24, that would be negative. If I plug in 3, I would get a positive. So I have 2 points of inflection. So I have positive, negative, positive. So points of inflection, I have one at 0. So if I plug 0 back in, I get 16. And I have one at 2, and if I plug 2 in, 2, 0, 0 plus 16, or -16, so that would be 0. Okay. So we're going to draw these points. So I have a relative min at 3, -11. Let's use a different color. That looks about like 11. Point of inflection at 0, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Nailed it right there. I've got one at 2, 0. Okay, so by my concavity, I'm going to have like this upward slope. So it's got a positive slope, or excuse me, not a positive, a negative slope when it's less than 0 with an upward concavity. So it's going to curve towards this. And then to 2, it has this downward, so it's kind of like John Travolta to 2. Okay, and then remember that 311 is like a relative min. Actually, an absolute min. It's going to curl and come back up. Go up. Sorry, that was not a great drawing, but that's supposed to be 3, -11 right there. That min. So it's, remember you have a x to the 4th, so it has kind of a W-ish, well, not very W-ish, but more parabolic look to it. Okay. All right, so I think that's pretty good help with those 2 problems, or 3 problems. Okay, so I want to see if you can do at least 4 and 5 on your own. This time, do notice that they ask you to find intercepts and then to graph it. All right, good luck.